that I find this is something I do quite a lot. Not necessarily just copying a file, but processing data from a file. You read something in from a file, you do something with it, you write it out to another file. Okay, we do that kind of thing a lot in applications. Here's a piece of code that would do something like that. So we create an input stream for our input file, we create an output stream for our output file, we then have a buffer of 8K, we have a number to record out how many bytes we've read, and then we simply read from the input stream and write to the output stream. Okay, so that's perfectly valid code in the sense that it will copy from one file to another. But because we're using input stream and output stream, these are what we call resources. And a resource is something that you explicitly open, you use it, and then you explicitly close it again. And in order for this code to be correct, you have to call close on the input stream and the output stream. That way you can guarantee that, certainly with the output stream, if there's any data in a buffer, when you call close, the data will be flushed from the buffer to the file. So we need to guarantee that we call close. So we could do that using a try finally block. That's a very typical way of doing things. So now we've got our input stream and output stream, and then within the try block, we put the code for our copy. And then we have a finally clause, which says that no matter what happens in terms of completion or exception in the try block, we will always get to our finally clause. So we call the input stream close, and we call the output stream close. So that's better, but it's still wrong. Because even though we guarantee that we will get to the finally clause, if we call the close on the input stream, and that throws an exception, we won't get to the close in the output stream, because the exception will actually bail us out of the finally clause. So the way to do that correctly, which I'm sure you would all do, is to nest the try finally blocks. So you end up with a situation where we create our input stream, we then have one try block within which we create the output stream, a nested try block where we actually do the copying, a finally block associated with the inner try block to call the close on the output stream, and then a finally block outside which calls the input stream. That way we guarantee that no matter what happens, whether we throw an exception in our copying code, we'll always call the close on the output stream, and no matter what happens there, we'll always call the close on the input. Now that in itself is not too bad, but if you think about it, that's reading from one file and writing to one file. What we might well be doing is reading from 5 different files to accumulate information, and then outputting to 3 different files to do something or other. So that would require us to nest 8 different try-finally blocks to do it correctly. And I don't know about you, but I would find that quite difficult to guarantee that I've got all the nesting correct and making sure that no matter what happened in terms of exceptions, all the close methods were called correctly. Now there's another problem with that, which is that if I throw an exception, let's say I'm using a network resource and somebody pulls out the network cable, I get an exception thrown when I try to write data to my output file, so that throws an exception. I then drop into my finally block, that calls the close on the output stream. Because that's no longer there, that's going to throw an exception as well. And then I get to my close on my input stream, and that's going to throw an exception as well. What I'm actually going to get in terms of the information reported back to me is only the exception from the last close. So I won't see anything about the exception that was thrown in the right, and I won't see anything about the exception that was thrown in the first close. The solution to that is, in Java SE 7, what we call try with resources. Now we've changed the syntax of the try statement. So you can specify a set of brackets after the try statement in which you can create references to objects of class which implements the auto-closable interface. Auto-closable is a new interface which is simply an extension of closable. And it doesn't add any new methods, so it's really just a marker interface on top of closable. Closable, funnily enough, has one method, which is close. So if you create references to objects here which implement the close method, and you don't have a finally clause, then the compiler will say, okay, no matter how many streams you're using here, I will guarantee to write the code correctly for you so that the try finally blocks are nested in terms of making sure that everything happens correctly. So you'll get to the point where you can guarantee that all of the different closes will be called, and you won't get to a point where you're not calling a close correctly. So that makes life a whole lot simpler, because now we can just have one try block no matter how many resources we're using. So a little bit of detail about that is the compiler does all the work for you, basically. It desugars the try with resources aspects of that. So as I say, we use the auto-closable interface, and you can actually use that in other places. It doesn't have to be just for things like input streams and output streams. So for example, in some of the locking that you can use in Java at the moment, if you use the concurrency utilities, you have to remember to call the unlock method on a lock. So if you implement the auto-closable interface on a class, which extends a lock, you can use the close method to guarantee that you unlock it, and therefore using the try with resources, you can guarantee that the finally clause will always unlock the lock for you. So that's another sort of interesting use of that. The other thing is that we've added the ability to get more information about the backtrace of the exceptions. So again, if you had this situation where you've got 3 different exceptions thrown, now rather than just getting the last exception information, what you'll get is a trace of all the different exceptions that were thrown. So if we throw an exception in the close of the input stream, close of the output stream, and the write, you'll see the data about all of those 3 exceptions that were thrown. Again, that gives you more information. You can see what actually happened in your application. var args. Now, in Java SE 5, we introduced a bunch of new features. We introduced the idea of generics, and we also introduced the idea of variable argument lists. Variable argument lists are something which has been in C and C++, well, forever. And it's something that people have got used to, and so it was decided that in Java we would add the same concept. So now you can have a method which takes a variable number of arguments. When you call that method and you pass a variable number of arguments, those arguments will be converted into an array of objects, and that will be passed to the method. So the method will receive an array of objects which you can then iterate over to get the arguments that will pass to the method. That's all well and good. The problem comes when you combine variable argument list methods with generics. One of the things we did with generics was to have backwards compatibility. And that made generics a lot more complicated underneath than you might think. So what actually happens when you use generics is that we do type erasure. And so we actually strip off all of the type information that you've added in terms of your type parameters. Some of it's maintained for compilation, but on the whole, it's all stripped off and it's not available at runtime. If you combine the fact that you've stripped off the type information with an array that you use in a variable argument list, you can get to a situation where you can write a completely valid piece of code. So this is a completely valid piece of code where we're using a variable argument list method, and we're using a generic collection which we're passing to that. The problem is that because the type erasure kicks in, and we're using our array as list, what we'll actually do is get a warning message from the compiler, because the compiler has done some things underneath, stripped off the information and says, oh, actually, that's an unchecked generic array creation situation. So your code is absolutely correct, but you're getting a warning message because of what the compiler is doing. So that's not a very desirable thing to have, because obviously you can't change your code to make that warning go away. It's, your code is correct, the compiler is the thing that's at issue there. So we've added a couple of things here to make your life easier. So now you can have some annotations, and you can say either at suppressed warnings value equals unchecked, or you can say at safe var args. And that way, if you get a warning and you look at your code and you say, well, there's nothing wrong with it, you can simply say to the compiler, well, I know I'm correct, turn off the warnings. Just be a little bit careful if you do use that, and to be honest, I think this is a situation that most people won't see very often, but if you do get a situation like that, you do have to be careful, because you have to be absolutely certain that the code that you're writing is correct. So otherwise you're turning off a warning, which may be a valid warning. Another thing that we've done is to tidy up some things around exceptions. So at the moment, if you want to have a piece of code which generates potentially a number of different types of exception, and you want to do different things with them, you have to explicitly place a catch clause for every type of exception. So here I've got a piece of code in a try block which can throw one of 4 types of exception. And for the class not found exception, I want to do something clever, but for the other 3 types of exception, instantiation exception, no such method exception, and invocation target exception, I want to do the same thing. But because I can't group those 3 together, because there's no common superclass for those exceptions, which wouldn't also include class not found exception, I have to put them as 3 separate pieces of code, 3 separate catch blocks. Now, in this case, that's not too much of a problem, because I can see very clearly, okay, I've got log of those exceptions, and that's easy. But if you had a situation where what you were doing in the exception was quite complicated, and you've got to replicate that 3 times, if somebody comes along and has to do some maintenance on that, maybe they look at the first exception that's being caught, they change the code there, and they forget to change it in the other 2 places. That way you get into a situation where you've got some very subtle bugs, very difficult to find, hard to maintain code. So now we've made life easier in Java SE 7, and we have the concept of a multi-catch block. All this does is it says, rather than having to have an explicit catch clause for each type of exception, if you want to do the same thing, you can simply say catch instantiation exception, or no such method exception, or invocation target exception E, and then you can log that exception. Of course, if you want to find out what the type of that exception is, then you can do that within the code. You can say, okay, well, is it an instance of instantiation exception, then do something. But that would probably be a bit silly, because if you're already grouping them together, you don't want to find out what the explicit type is at some point later. So that's really the key things in terms of the language changes. So let's look at the changes to the library, or libraries, and what we did there. Now, probably there's 2 really big areas. One is the input and output libraries. And back in the very early days of Java, we had the Java I/O APIs. So we had the ability to read from files, write from files, write to files, and so on. But these I/O libraries were not really designed, well, let's say terribly well. They certainly weren't designed to be extensible. A lot of them were final, wasn't easy to extend classes, things like that. A number of methods don't throw exceptions in the way that you actually think they would. A lot of methods actually return something as a Boolean to say whether it completed or successfully or not. So rather than throwing an exception where it should do, it returns a Boolean. And that makes life, inconsistent and complicated, and goes back to what Chuck was saying about making your life difficult as a developer. Things like the rename method works inconsistently across platforms. Metadata for files is something that developers want access to, and that's not been dealt with particularly well. One of the things you have to think about is that these libraries were designed back in early 1990s, so nearly 20 years ago, and so things were very different in terms of operating systems back then. We did introduce the NIO libraries, the new IO libraries, and then what we've done now is to introduce the NIO2 libraries to solve a lot of these problems. Some of the main features of the NIO2 libraries is that currently, if you look at file interactions, you use the file class. Because we couldn't extend that easily, we couldn't replace the methods that we needed. Sorry, I'll wait. No rush.
AKB48. Yes.
Okay. So Chuck and I have worked together for a long time. So we couldn't extend file, and so the easiest thing to do was to create a new class to replace where you would use file. So that now you would use path rather than file. A lot of it is very similar in terms of functionality, but it adds a lot of new features as well. Much better support for directories, so the idea that you can now have an iterator for getting a list of the, well, you can stream things via an iterator for a list. I'll talk a bit more about that in a moment. And you can filter using regular expressions to say, okay, I only want these particular named files and things like that. Proper symbolic link support. Now that all common file systems support the idea of symbolic links, then we can make that part of the standard package. We have the idea of an extendable file system package, and that allows you to do some interesting things with, like treating a zip file as if it is a file system. So you don't have to unzip it, you can actually just access it as if it was a file system and get the files within it. And also an attribute package so that we can get more information about the metadata associated with files. So the path class, as I said, is really the equivalent of a file class as we use at the moment. And a lot of where you use file at the moment, you just replace it with path. And there's different ways you can create paths. So you can say, okay, path home equals paths, because paths is the utility class, .get/home/Fred, and then you can resolve the reference from Fred to the temp directory within Fred, using the same thing with resolve. And you can also create a relative path where you're going, up, using ... to go up, and then down, things like that. So there's different ways to access the path information and create references to files in the way that you want to. Now, this is probably one of my favourite features in Java SE7. And once again, I stand here a little embarrassed to say that it has taken us 16 years to get to the point where we can actually have a single method call that will copy a file. You really got to wonder, haven't you? It's taken us that long to get to a method that will copy a file. But this is what we can now do. So we can create a path, reference to a file and a reference to a copy, and then we can say I want to copy that file from one place to another. And we can also add some extra information to say we want to copy the attributes of the file, and we also want to replace an existing file if there's one there. We also can do a move, so we don't actually just have to do a copy, we can also do a move, and we can do it as an atomic move so that it becomes an atomic operation within the file system. Yes, directories, like I say, there's some useful improvements around directories. One of the problems that we had with directory listings as it stood previously was that if you wanted to get a list of files in a directory, the method that you called would block until all the directory entries had been read underneath. That's fine if you've only got 20 files in a directory on your hard disk, it won't take very long. But if you're reading 100,000 entries across a network, it's going to take a long time to come back. So what we now do is have the idea of a streaming system. So you can open the listing of the directory entries and you can get them as they arrive. So you're not waiting for them all to be buffered before you actually start getting them. Implements iterable, implements closable. So again, you can use the same syntax we have with try with resources. So here I can now say, okay, create me a path to home Fred source, and then get me a, so we're going to use a try with resources here. So I do a try, create a reference to a directory stream of type path, which gives me a new directory stream, and I'm using a wildcard to say all the Java files within that, and then use the for path file over the directory and say, here's the file name. And that will give me all the information that I need. And I guarantee that when I leave that block, of course, because it's implementing the auto-closable interface, it will actually close the directory stream for me. Concurrency APIs. This is back
to the slides. How's the implementation strategy of directory stream?
In what sense?
I mean, is it featuring one file or things when it's iterated to that entry? Or?
Okay, so what you do is you create a reference to a directory stream of type path, and when you do the iteration over that, basically what it's saying is that won't block until the entries have loaded. So when you do for file over directory, it will just read them as they come in. So as soon as one is ready, you'll see it printed out. And
so,
then
so there will be a backend thread that is keeping lookup.
Yes,
okay.
absolutely. So the other big side of the library extensions was the idea of concurrency APIs. And if you think about the way that concurrency works in Java, we've always had the idea of threads in Java right from the very beginning. But it's not been terribly easy to write multi-threaded code that's reliable because you've had very primitive operations like sleep, wait, notify, and interrupt. Java SE5 introduced the concurrency utilities, which introduced lots of new features like semaphores, mutexes, rewrite locks, things like that, which were very useful higher level features that could actually enable you to write more reliable code. In Java SE7, we had an extension to that, so JSR 166 was the original release. JSR 160X for extension was the one that came out of Java SE6, and then how people come up with these ideas I don't quite know. But they decided that JSR 166 should be extended further, so rather than being X for extension, it's now Y, because Y is the next letter after X. Go Y. Yeah, Y, exactly, Y. So what we added there was a few things. The big thing is the fork join framework, which allows you to break up tasks into subtasks, and we'll talk a bit more about that. There's also a concept of like a phaser, which is another high-level construct, similar to like a cyclic barrier and a countdown latch. And there's a transfer queue, which is like a blocking queue, but you can decide that you want to transfer an object into the queue and then wait for it to be processed, or you can say, no, I don't want to wait for it to be processed. It's just adding some more semantics, really, to how a blocking queue works. So the idea behind the fork join framework is that you have some kind of task that you want to be completed, and that task can be easily broken up into a number of subtasks. Those subtasks, in order to work well with the fork join framework, should be independent of each other. So they shouldn't rely on common data where you have to share the data between them and you get involved in locking and contention. So if you've got a task where you can break it up into independent subtasks, then fork join is very good for that. And the idea is that you apply this recursively. So you take a large task, you break it up into, let's say, 2 smaller subtasks. Those subtasks you can then break up into 2 smaller subtasks, and you keep doing that until you get to the point where the subtask is a small enough unit that you think, right, I can process that easily. And so the algorithm is, if I can manage the task, perform the task, it's small enough, else fork it into a number of smaller tasks, and then when you get all the results back, join them together. So really the idea behind fork join is to enable you to do that kind of thing with that algorithm, but without having to handle all the complexities of generating a number of threads, allocating the jobs to the threads, and then having the threads all coordinated so the results are available at the same time, joining them all up and providing the result. So from the programming point of view, you simply say, okay, here's my task, here's how I want to divide it up, here's my criteria for what is a small enough task, and give me the result. So the typical classes that we're going to use in this is one, a fork join pool, and this is where the system will create a pool of threads that are going to be used to process your tasks. And typically what that's going to do is create as many threads as you have processors available on your machine. The processor really is threads available in the operating system. So if you can do your hyper-threading, then that would count as well. You then have the concept of a fork join task, which is really an abstract class, and is the base class for what we're actually going to do. And then you either use a recursive action or a recursive task. Both of those are subclasses of the fork join task, and a recursive action does not return a result, whereas a recursive task does return a result. So if you need some result to be returned as part of your completion, then you use a recursive task. If you're, say, writing something to a file as a result, and you don't need to return a specific result, then you would use a recursive action. Both of these implement a compute method. So you, as the developer, write the compute method to say what it is that that task is going to do. So I use a somewhat trivial example, but is useful to show how the concept works, is to calculate the Fibonacci sequence. So what we're going to do here is simply say, okay, I want to create something to calculate the Fibonacci sequence, and that's going to extend a recursive task, and we use type parameters to say that the result is going to be of type integer. We have a final int, which is the number, and then we have the Fibonacci constructor, where we take the number, which is what we're trying to calculate the Fibonacci sequence of. We then implement the compute method, and we simply say if the number is 0 or 1, we return 0 or 1, and then if it's not, then we need to calculate some subtask. So we create two new subtasks, so we fork off into two subtasks for the Fibonacci of number minus 1 and Fibonacci of number minus 2. We fork those new tasks off, and the framework will handle that for us, and then we return the result of the first fork joined with the second fork join result. So the join method will only return when the result is ready. So we know that it's very easy to coordinate that when f1.join and f2.join are ready, because either of those methods will block until the result are ready. And when both ready, add them together and return, and then that will return to somewhere higher up in our recursion.